Hello, in this video we're going to be talking about limits of sequences. Well, this is calculus after all, and yet we've not done much actual calculus in this unit yet. The only calculus that we can really apply directly to sequences is to see if an infinite sequence has a limit as the input variable k approaches infinity. This is defined in essentially the same way that limits going to infinity were defined for functions in general. The only thing that's changed is the notation for the output. And of course the fact that the input is only the natural numbers. So here's the actual definition right here. We say that a limit as k approaches infinity of a sub k equals some number L, L's the limit, if and only if for any epsilon greater than 0 there exists a positive number m such that if k is greater than m, then a sub k minus L, absolute value of that, is less than epsilon. In this case, we say that the sequence converges to L. If the limit does not exist, then we say the sequence diverges. In other words, no matter how small an error, epsilon, that you want to check for, there is a number, m, such that for all k's bigger than m, the terms are close to the limit. How close? Well, within that epsilon. So I created this activity to in Geogebra to investigate that, and I think I have it open here. Let me pull that open. Yeah, so here it is. So you can enter a formula into this little box here, and just you can make it as a formula as a function of k, and it's a sub k. Figure out what the limit is and place that there. If you change the limit, I'll change it to something that's wrong. It changes where this center line is here. Okay, put it back to the actual limit, which is 3 in this case. And you can change epsilon either by this slider or by typing a number in here. Okay, and so what you want to do is for a particular epsilon, there should be an m somewhere in here. It could be you could always make m be a natural number if you want, or you could make it be anything. But there's some point, actually, if we go in between these 2 points, or anything after this point for m, we see that all the points are within this blue region. See, let's go even further if we want to be more clear about it. But from some point on, all the values stay within where this blue region. What is this blue region? Well, it's the region between y equals the limit minus epsilon. So this distance from this line here is that line is the L. From it down to this is epsilon, and from that line up to this line, the top is L plus is also epsilon. So the bottom line down here is L minus epsilon. The top is L plus epsilon, and then of course it's to the right of m. It's kind of like a rectangle, but it goes forever in the right direction. Okay, and these points will always stay inside of there. And the point is, what happens if we make this smaller? Well, we've got some points outside here. Well, we just pick a bigger m. But there's some point out here. From there on, all of the points are inside that region. And no matter how small we make this, then there is an m somewhere out here, so that the points from there on are within that. And if we were to do this right, we could go further, do it correctly. We could go further and further out to the right. If we take smaller and smaller epsilons, we just go further and further out to the right for m. And that's what's meant by having a limit there. And of course, these are getting closer and closer to that, kind of like an asymptote. Yeah. Okay. So let's look at. There's a static picture of that. So now it's time to do an exercise. So we've looked at arithmetic and geometric sequences in the last couple of videos. Do they have limits? And if so, what are they for an arithmetic and a geometric sequence? See if you can figure that out yourself. Press pause now. Well, you should realize that there's no way an arithmetic sequence is ever going to have a limit. Since we're recursively just adding the constant m each time to get each successive term, the sequence will diverge to infinity if m is positive, and will diverge to negative infinity if the common difference m is negative. Okay, so if you take the limit as k goes to infinity of mk plus a sub 0, it's infinity for positive m's and negative infinity for negative m's. So, like say if the slope was 2, whatever that first term is, you'd add 2, and then add 2 more, and add 2 more, and add 2 more, and add 2 more. It's just getting bigger and bigger and bigger. So it increases without bounds. It has no limit at all. Either way, the limit doesn't exist, so the sequence diverges. Now here you notice we skipped m equals 0. If m equals 0, this arithmetic sequence really isn't arithmetic anymore. It degenerates down to a constant sequence, and that, of course, that does have a limit. For whatever that first term is, all the terms are the same, and of course that's the limit. But if we ignore that degenerate setting, every truly arithmetic one never has a limit. If we have a geometric series, it's going to converge to 0 if and only if that base or the common ratio, b, or the base, is a number that's between -1 and 1, exclusive. In other words, its absolute value of b is less than 1, and it's going to diverge otherwise. So if the k is going to infinity, and our sequence is a sub 0 times b to the k, which is the form for a geometric series, one way to write that. If the base is small, we've got exponential decay, and it's going to approach 0. How small? Well, less than 1. Absolute value less than 1. But it doesn't exist otherwise. Now, we are making one assumption here that b is not 1. If b is 1, then every time we're just multiplying by 1, that means we have a constant sequence, and we're not going to really count that as being a geometric sequence. So that, of course, a constant sequence converges again. Okay, let's introduce a couple of terms here. A sequence is monotonic if and only if it is always non-increasing or non-decreasing. Monotonic sequences include increasing sequences in which each term is greater than the previous term, and also they could include decreasing sequences in which each term is less than the previous term. Monotonic sequences always go basically in the same direction. So, for example, a non-increasing monotonic sequence may have some repeated terms, of course, which don't change, but otherwise the terms have to go down. So they're either going down or staying the same for a monotonic non-increasing. Monotonic non-decreasing would be going up or staying the same. A sequence is bounded above if and only if the terms are always less than some constant, which we call the bound. A sequence is bounded below if and only if the terms are always greater than some bound, and a sequence is bounded if and only if it is both bounded above and bounded below. And bounded monotonic sequences must converge. You can have some that don't converge that are bounded, but they're not monotonic. You can have some that are monotonic but are not bounded, and they might not converge. But if it's both bounded and monotonic, it's got to converge. So here are a few. Let's see if we can find some limits. Now, remember, you can use all your tricks from Calculus 1 on limits here as well, right? So here's several examples. The first one, a sub k is 3k plus 1. Second one, a sub k is 2 to the k over 3 to the k. Part C is a sub k equals a fraction. The numerator is 2k squared plus 3k minus 1. The denominator is 3k squared plus 4k minus 7. D is a sub k is sine of k pi. E is the sine of k times pi over 2. F is a sub k equals sine of k divided by k squared. And in G, a sub k is k cubed over e to the k. See if you can work those out. Come back and we'll go over them. Press pause now. Okay, so we're going to be using a lot of the things that we found back in Calculus 1, and we're going to introduce a few, just remind you of a few techniques. So certainly the limit of 3k plus 1 is k goes to infinity is infinity. That's an infinite arithmetic sequence like we just talked about. And 2 to the k over the 3 to the k can be rewritten as 2/3 to the k. So that's just an infinite geometric sequence with a base between -1 and 1. So it is in fact a convergent, like exponential decay sequence, geometric sequence, so it converges to 0. All right, one of the ways there's multiple techniques here perhaps, but one of the ways we can figure out this next one is multiply the numerator and denominator by 1 over k squared and distribute. That gives us this form here, 2 plus 3 over k minus 1 over k squared for the numerator. The denominator is 3 plus 4 over k minus 7 over k squared. Then take the limit of each piece. All these parts with k go to 0, and you're left with 2/3. And this next one, which was the sum of, or a sub k is sine of k pi, okay, is it's an example of the difference between a sequence and functions whose domains is a set of real numbers. So one more thing we can say in general is if f of k equals a sub k for natural numbers k, but f is also defined, say, for all real numbers greater than 1, then the limit of f of x as x approaches infinity is L. If that's true, then the limit of a sub k as k approaches infinity is also L. So sometimes that's useful. However, there are examples where f of k equals a sub k for natural numbers. F is defined for all real numbers greater than 1, but the limit as the limit of f of x as x approaches infinity does not exist, but the limit as k approaches infinity of a sub k does exist in spite of this. And this is an example exactly of that. Okay, in this example, the limit of, let's see, this is actually the sine of pi x is our function, f of x, right? And the limit as x goes to infinity of that does not exist since it's always bouncing up and down between all values, y values between -1 and 1 to the right of any x value, right? So that limit just does not exist. However, this sequence doesn't take on all those values between -1 and 1. In fact, it's just a constant sequence. If you plug in natural numbers for k, any natural number multiple of pi, in fact, any integer multiple of pi, when you take the sine of that, you get 0. So this is just the sequence 0, 0, 0, 0, 0, right? So the sequence definitely converges to 0. Now the next one, when you do sine of k times pi over 2, you actually get a 4 number repeating pattern. When putting k is 1, sine of pi over 2 is 1. K is 2, that's the sine of pi, which is 0. K is 3, that's the sine of 3 pi over 2, which is -1. And k is 4, that's the sine of 2 pi, which is 0. And then the whole thing repeats over and over and over and over and over and over again. So this is a 4-digit or 4-number repeating pattern that continues on forever, and certainly that has no limit to it. Another thing that we can use sometimes is the squeeze theorem, if I remind you about that. Notice that sine of k is always between -1 and 1. 1 over, so that means if I divide everything by k, which is a positive number here, -1 over k is less than or equal to sine of k over k squared, which is less than or equal to 1 over k. And so that means the limits are between. So the limit of -1 over k is less than or equal to the limit of sine of k over k squared, which is less than or equal to the limit of 1 over k. All those as k limits as k goes to infinity. Well, the ones on both sides, both ends, are certainly 0. So that means the one in the middle gets squeezed. It's also 0 as well. So there's the squeeze theorem. Remember L'Hopital's rule? Now, technically speaking, L'Hopital's rule doesn't apply here because these are not continuous functions here. But we can use this thing that we set up earlier, that if a limit exists for this function that agrees at all the natural numbers with the original one, then the limit has to exist for a sequence, and it's the same thing. So we can use that this way. So for example, this one we had the limit as k goes to infinity of k cubed over e to the k power. Well, if it exists, this limit on the right is the limit as x goes to infinity of x cubed over e to the x. Now, it may just look like I just changed letters, but I'm meaning more than that. On the left, I'm assuming k is a natural number. On the right, I'm assuming k is any real number, well, a big one at least, okay? And so now, this has the form infinity over infinity, so we can use L'Hopital's rule. Since I made this a continuous function of x here on the top and bottom of the fraction, I can do, it's actually a differentiable function, so I can take the derivative. So the derivative of x cubed is 3x squared. The derivative of e to the x is e to the x. Well, now I do that limit, and it's still going to infinity over infinity, so I'll use L'Hopital's rule again. And so the derivative of 3x squared over the derivative of e to the x, well, that's 6x over e to the x. Again, it's the form infinity over infinity. So for a third time, I apply L'Hopital's rule. And the derivative of the top is 6, and the derivative of the bottom is e to the x. And now we see that the bottom goes to infinity, but the top is constant. So now that goes, we know that that limit is 0. Since that limit is, so they kind of work backwards, since all these limits are, that limit exists at the end, all these other limits are 0 as well. Okay, let's keep talking here real quickly about function dominance just a bit. This idea of L'Hopital's rule kind of gives us something that we see sometimes. So often in our study of sequences and series, we find ourselves computing the limit of a sequence whose formula can be written in the form of a fraction. And often both the numerator and denominator approach infinity as the input variable is increased, or work the same if they both approach 0. So L'Hopital's rule is then applied to determine a limit, or switch to x's first, and so forth. After some study of functions of this type, we can determine that there's a hierarchy of speed with which certain classes of functions approach infinity. For large values of the input variable, we have the following. Logarithmic functions, well, first of all of these functions that I'm getting ready to list are going to approach infinity. But here is an order to how fast they go. Logarithm functions approach infinity, but for large x's, they are much smaller than so that symbol means significantly less than. Power functions with positive powers less than 1. So these are increasing concave down, but the power function will eventually dominate. Then polynomial functions are going to always grow faster than that. A higher degree polynomial function will grow faster than a lower one. Exponential functions, or geometric sequences, with a base larger than 1 will grow faster than that. And then factorial functions are really fast. They even grow faster than exponentials eventually. So here the double less than means significantly less than. I'm not going to try to make that real precise, but basically what that's saying is as we get x gets x or k, the input gets bigger and bigger and bigger, then the outputs are going to be, well, the one on the right is way bigger than the one on the left. It leaves it in the dust. Okay, so the ones later in the list approach infinity significantly faster than those earlier in the list, and kind of L'Hopital's rule can kind of help us explain that, as we kind of saw in our last example. But we say that the later function types dominate the other earlier ones. For example, if we have a sequence whose formula is a polynomial sequence divided by a geometric exponential sequence, then the geometric portion will dominate, and the sequence will have a limit of 0. So the bottom getting big makes the fraction want to go to 0. The top getting big is pushing it toward infinity. In this case, it's the bottom that dominates, so it's going to have a limit of 0. For another example, if the function is a factorial function divided by an exponential, the factorial function will dominate and the sequence will diverge to infinity. Okay, probably some time to, well, at least the textbook we're using this semester, it's time to read your textbook, the first section, and you should have some homework problems to get caught up on and work on the first homework set.